Before there was light, before gravity curved the first thread of space-time, before matter took its first trembling step into existence, there was silence. Not the silence of an empty room, nor the quiet pause between heartbeats, but something deeper, something absolute, a stillness so complete that even the concept of sound had no meaning, for there was nothing to vibrate, nothing to carry a wave, no distance for echo to travel. This was the silence before geometry, before dimension, before the universe learned to measure itself, and yet, within that nothingness, something stirred. Not motion. Motion requires space. Not time. Time had not yet been born. But potential. Pure unmanifested possibility. Humming beneath the surface of non-existence, like a held breath before the first word. Physicists call this the quantum vacuum. A sea of virtual particles flickering in and out of being, borrowing energy from nowhere and returning it before the cosmos could notice the debt. But even this description fails because it uses words like before and nowhere, concepts that only make sense after creation has already begun. Imagine standing at the edge of all edges, where reality has not yet decided to be real. No stars watch you, no darkness surrounds you, because darkness itself is something, an absence that requires space to be absent from. Here there is only the pregnant pause, the cosmic inhale before the longest exhale in existence. And in that silence, the story of the universe begins. We use the word nothing casually, thoughtlessly. An empty cup, a blank page, a room with no furniture. But these are not nothing. They are containers waiting to be filled, spaces defined by the walls that bound them. True nothingness is something the human mind cannot fully grasp, because our consciousness is built from some things: neurons firing, memories layering, thoughts emerging from the electrochemical dance of matter. To imagine nothing is to ask the universe to forget itself. Physics offers us a glimpse into this impossibility. The quantum vacuum, what we might call empty space, is not empty at all. It seethes with virtual particles, pairs of matter and antimatter spontaneously appearing and annihilating in time frames so brief they exist in the shadow of measurement. Energy fluctuates here, governed by Heisenberg's uncertainty principle, which tells us that even in a perfect vacuum, something must be happening. The universe, it seems, abhors true nothingness the way nature abhors a vacuum, by filling it with potential. But before the Big Bang, even this quantum foam did not exist. There was no space-time for particles to borrow, no framework of physical law to constrain their behavior. The absence was more profound than physics currently describes. No dimensions, no duration, no where or when. Imagine trying to describe the color of a sound to someone who has never experienced either. This is the challenge of describing the state before existence. Philosophers have wrestled with this paradox for centuries. How can something come from nothing? The question itself may be flawed, assuming a transition that requires time, a before and after. But if time itself emerged with the universe, then before is a meaningless word. Perhaps the universe did not come from nothing. Perhaps it is nothing organized. Perhaps existence and non-existence are not opposites, but perspectives, two sides of a coin that has not yet been minted. And perhaps in trying to imagine absolute nothingness, we are asking the one question the universe was designed never to answer. There is a moment in the story of creation where equations fall silent. Not because they are wrong, but because they reach the boundary of their own meaning. This moment occurs at the Planck era, the first 10⁻⁴ seconds of cosmic history, a duration so brief that light, traveling at its cosmic speed limit, could only cross a distance smaller than a proton. Here, at temperatures exceeding 10 degrees Kelvin, the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single primordial force. Space and time themselves dissolved into quantum foam, where the smooth geometry of Einstein's relativity meets the probabilistic chaos of quantum mechanics, and neither theory can fully describe what happens next. Einstein showed us that space and time are not separate entities, but woven together into a single fabric, curved by mass and energy. His equations predict that, if we wind the clock backward, tracing the expansion of the universe in reverse, we arrive at a singularity, a point of infinite density where the laws of physics break down completely. But Stephen Hawking, along with Roger Penrose, proved mathematically that singularities are not just mathematical curiosities, but inevitable consequences of general relativity. If the universe began from a Big Bang, then it emerged from a state where space was compressed to zero volume and time had no meaning. Yet Hawking himself later questioned this conclusion. Applying quantum mechanics to the earliest moments, he proposed that time might behave differently at the cosmic beginning, not as a straight line with a definite starting point, but as a curved surface with no edge, like the surface of a sphere. In this model, asking what came before the Big Bang is like asking what lies north of the North Pole. The question dissolves not because we lack an answer, but because the question itself becomes meaningless once we understand the geometry of space-time near the origin. This is the frontier where human knowledge encounters its own reflection. We have maps of the cosmic microwave background, the afterglow of creation. We have equations describing the behavior of particles in the first fractions of a second, but the instant of emergence, the transition from nothing to something, or from one state of reality to another, remains veiled. Perhaps necessarily so, for if time and space emerge together, then causality itself, the idea that events unfold in sequence, is a feature of the universe, not a precondition for it. The universe might not have a cause in the way we understand causes. It might be its own explanation, a self-contained loop of existence that simply is, without requiring permission from anything outside itself. And so we arrive at the first question, the one that echoes through every chapter of cosmic history. Did the universe truly begin, or did it transform from something we cannot yet name? Perhaps the Big Bang was not a moment of creation, but a phase transition, like water turning to steam, a change in state rather than a birth from nothing. Perhaps what we call the beginning was simply the moment when the universe became knowable to itself, when the laws of physics crystallized from a more fundamental reality that operates by rules we have not yet discovered. This question unsettles us because it touches the deepest human yearning to know where we came from, to trace our lineage back to the very first ancestor. But if the universe has no beginning in the conventional sense, then we are children of a cosmos without birth, participants in a story that has no first page. We are not the result of a creation, but the continuation of an existence that might be eternal, not in the sense of lasting forever, but in the sense of existing outside time altogether. Consider this: every moment we experience, every memory we hold, every thought that passes through our minds is made possible by the fact that the universe once condensed all of space-time into a volume smaller than an atom. The laws that govern the fall of an apple and the orbit of galaxies emerged from that unimaginable density. The elements in our bodies were forged in the hearts of dying stars, which themselves were born from hydrogen clouds that condensed under gravity. Gravity that only exists because space-time knows how to curve. We are not separate from this story. We are the universe examining its own origin, asking questions it may not be able to answer, but which it cannot help but ask. What if creation was not an event, but a property? What if existence is not something the universe does, but something it is, an eternal present that only appears to unfold because we experience it from within time? And if that is true, then the sound before sound was not silence waiting to be broken, but the universe listening to itself before it learned to speak. In the first fraction of a second, a period so brief that all of human history compressed into it would still leave room for billions of years, the universe was not a place, but a condition. Energy and matter had not yet separated into distinct entities. Particles and antiparticles materialized and destroyed each other in a cosmic furnace where temperature and density defied comprehension. This was the realm of the quark-gluon plasma, a state of matter so extreme that protons and neutrons could not yet form. The fundamental forces, once unified, began to separate like streams diverging from a single source. Yet even in this chaos, there was order. Einstein's field equations, written decades before humanity had any evidence of the Big Bang, predicted precisely this, that space-time itself is dynamic, capable of expanding, contracting, and carrying the universe forward. The singularity was not an explosion in space, but an expansion of space itself, carrying energy outward, not into emptiness, but creating emptiness as it went. Every point in the universe was once the same point, and in expanding, every point carried with it the memory of that unity. Within the first second, the temperature dropped from trillions of degrees to mere billions. Quarks bound together to form protons and neutrons, matter and antimatter, annihilated each other in nearly perfect symmetry, but a tiny asymmetry, one extra particle of matter for every billion pairs, ensured that something would remain after the annihilation ended. This imbalance, unexplained and essential, is the reason galaxies exist, the reason stars burn, the reason you are here to wonder about it. And through it all, space-time stretched, cooling and thinning, transforming from a dense symphony of energy into the vast, dark stage upon which the cosmic drama would unfold. But what is time? We measure it with clocks, mark it with calendars, feel it in the aging of our bodies and the changing of seasons. Yet Einstein revealed that time is not an invisible river carrying us forward, but a dimension woven into the fabric of reality itself, as real and as flexible as space. In his theory of relativity, time bends near massive objects, slows for those traveling at high speeds, and can even stop entirely at the edge of a black hole. Time, Einstein showed us, is relational. It exists between events, not as an absolute backdrop against which events occur. Before the Big Bang, there were no events, no particles colliding, no energy transferring, no change of any kind. And without change, time has no meaning. Time is not a container that existed before the universe and then was filled with cosmic history. Time is a feature of the universe, emerging with it, inseparable from it. To ask what happened before time began is to ask a question that language allows, but logic does not. Imagine a universe with only one particle, perfectly still. Would time exist? There would be no motion to measure, no change to observe. Now imagine a second particle appears, and they move toward each other. Suddenly, there is a before and an after. There is duration. There is time. Einstein's insight was that time is this relationship. The geometry that connects events, the structure that allows cause to precede effect. In the first moments after the Big Bang, as energy cooled and particles formed, time began to behave as we understand it. Linear, directional, irreversible. Entropy, the tendency of systems to move from order to disorder, gave time an arrow, a direction. The universe could expand, but not contract back to its origin, without violating the second law of thermodynamics. Time became the dimension along which complexity could emerge, along which the universe could evolve from simplicity to structure, from energy to matter to life to thought. Time was not created. Time was born, an emergent property of a universe learning to remember itself. For nearly 380,000 years after the Big Bang, the universe was opaque. Photons, particles of light, could not travel freely, because space was filled with a hot plasma of electrons and protons, constantly scattering and absorbing any light that tried to pass through. The cosmos was luminous but blind, glowing with energy but unable to see itself. Then, as expansion cooled the universe below 3,000 degrees Kelvin, electrons and protons combined to form neutral hydrogen atoms. In that moment, light was set free. Photons that had been trapped in an endless dance with matter suddenly found the universe transparent, and they streamed outward in all directions, carrying with them the image of the infant cosmos. This is the light we call the cosmic microwave background, the afterglow of creation, cooled by expansion from visible light to microwaves, but still detectable, still whispering the story of those first moments. Edwin Hubble, peering through his telescope at distant galaxies in the 1920s, discovered that they were all moving away from us, and the farther they were, the faster they receded. This was not because galaxies were flying through space, but because space itself was expanding, stretching the fabric of reality and carrying galaxies along with it. Hubble's discovery transformed cosmology from philosophy to science, giving us the first observational evidence that the universe had a history, a beginning, a story that could be traced backward to a point of origin. That first light, now stretched and redshifted by billions of years of expansion, fills the universe evenly in all directions. It is the oldest thing we can see, a snapshot of the cosmos when it was smooth and simple, before gravity had time to pull matter into stars and galaxies. Encoded in its tiny temperature fluctuations, variations of only 1 part in 100,000, are the seeds of all structure, the quantum ripples that would grow under gravity's patient hand into the cosmic web of filaments and voids we observe today. Light, it turns out, is not just what allows us to see the universe. Light is the universe's memory, carrying information across space-time, preserving the past in the present, linking the moment of creation to the moment you read these words. But here is the paradox that haunts every clock, every calendar, every attempt to measure time's passage. We do not experience time as a dimension. We experience it as flow, as becoming, as the relentless movement from past through present into future. Physics tells us that time is a geometric property of space-time, that past and future exist as surely as up and down, that the flow of time might be an illusion created by consciousness. Yet we cannot shake the feeling that time moves, that we are carried by it, that the present moment is somehow more real than the past we remember, or the future we imagine. What if time does not flow? What if we flow through time, like travelers moving through a landscape where past, past, and future all exist simultaneously, but our consciousness can only illuminate one moment at a time, like a flashlight beam sweeping across a dark room? This is the block universe, a model suggested by relativity, in which all moments are equally real, and the passage of time is simply the experience of a consciousness that can only perceive one slice of space-time at a time. Or what if time is not a thing at all, but a perspective, the way change looks from the inside? The universe does not move through time. The universe changes, and time is the language we use to describe that change. The clock does not measure time, the clock is time, a system evolving, a structure accumulating entropy, a mechanism that embodies the arrow pointing from order toward disorder. And we, composed of matter that once knew no time, now live within time, so completely that we cannot imagine existence without it. But perhaps we misunderstood it all. Perhaps time was never born. It simply began to breathe, and we are the breath. Every atom in your body is a messenger from the past. The hydrogen in your cells, the most abundant element in the universe, was forged in the first 3 minutes after the Big Bang, when temperatures were still high enough for nuclear fusion to occur, but low enough for protons to bind with neutrons. The carbon that forms the backbone of every molecule of life, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of these were created billions of years later in the cores of massive stars, where gravity compressed matter to densities and temperatures extreme enough to fuse lighter elements into heavier ones. When those stars exhausted their fuel, they collapsed and exploded as supernovae, scattering their enriched contents across space. Shock waves from these explosions compressed nearby gas clouds, triggering the formation of new stars, new planets, new possibilities. You are made of stardust not as metaphor but as fact, a literal truth written in the periodic table. Every element heavier than helium was created in stellar furnaces or in the violent collisions of neutron stars, those dense remnants of supernovae where matter is compressed to the point that electrons and protons merge into neutrons. But matter is more than a collection of elements. It is a record. The isotopic ratios in ancient rocks tell us the age of Earth and the conditions under which it formed. The distribution of elements in distant galaxies reveals the history of star formation across cosmic time. The structure of the cosmic microwave background encodes the density fluctuations of the early universe, the seeds from which all structure grew. Matter does not simply exist in the present, it carries within it the entire history of its creation, transformation, and journey through space-time. The universe remembers itself through matter, and we, composed of matter, are part of that memory. A way for the cosmos to look back at its own origins and wonder how it came to be. Yet matter alone could not have created the universe we see. Left to itself, matter would have remained evenly spread, a thin gas expanding into an ever larger void, cooling toward absolute zero, never condensing into stars or galaxies or anything capable of sustaining complexity. What shaped the universe was gravity, the weakest of the four fundamental forces, but the only one that operates across infinite distances, never diminishing in reach, only in strength. Gravity is the patient architect working across billions of years to gather matter into filaments and clusters, pulling gas clouds into stars, compressing star cores until they ignite in nuclear fire. But there is something strange about the way galaxies move. In the 1970s, astronomer Vera Rubin observed that stars at the edges of spiral galaxies were orbiting just as fast as those near the center, even though visible matter was concentrated in the galactic core. According to Newton's laws, stars farther from the center should orbit more slowly, just as planets farther from the sun take longer to complete their orbits. The only explanation was that galaxies contain far more mass than we can see, mass that does not emit, absorb, or reflect light. This invisible substance called dark matter makes up approximately 85% of all matter in the universe. We do not know what dark matter is. It does not interact with electromagnetic radiation, so it cannot be seen directly. It is not made of atoms, as we understand them, yet its gravitational influence is everywhere, holding galaxies together, bending light from distant sources, shaping the cosmic web of structure that spans the universe. Dark matter is not an error in our observations, but a fundamental component of reality, a reminder that the universe we can see, the stars, galaxies, planets, and light, is only a small fraction of what exists. The rest is hidden, not from light, but from all forms of detection, except gravity, that most ancient and universal of forces. And gravity, acting on both visible and dark matter, continues the work it began in the first moments after the Big Bang, organizing chaos into order, transforming uniformity into structure, sculpting emptiness into a cosmos. The universe does not expand into emptiness, it carries emptiness with it. Space itself stretches, and embedded within that expanding space-time is the oldest light in existence, the cosmic microwave background. This radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1965, is the afterglow of the moment when atoms first formed and light was released to travel freely through space. It fills the universe evenly, arriving at Earth from all directions with nearly uniform temperature, cooled by expansion from thousands of degrees to just 2.7 degrees above absolute zero. But nearly uniform is not perfectly uniform. Mapped with increasing precision by satellites like COBE, WMAP, and Planck, the cosmic microwave background reveals tiny fluctuations, regions slightly warmer or cooler than average, differing by only 1 part in 100. These fluctuations are not random noise, but the imprint of quantum fluctuations in the earliest moments of the Big Bang, stretched to cosmic scales by inflation. a brief period of exponential expansion that occurred in the first fraction of a second. These tiny density variations, amplified by gravity over billions of years, grew into the galaxies, clusters, and superclusters we observe today. The cosmic microwave background is more than evidence of the Big Bang. It is a fossil, a preserved moment from the universe's infancy, and like all fossils, it tells a story. It tells us the age of the universe, 13.8 billion years. It tells us the geometry of space flat, extending infinitely in all directions. It tells us the composition of the cosmos, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Most profoundly, it tells us that the universe we inhabit is not static, but evolving, not eternal, but historical, not designed, but emergent. The echo of expansion is still sounding, a cosmic whisper that reaches us from a time when the universe was smaller than a galaxy, hotter than a star, and simpler than we can imagine. And in listening to that whisper, we are doing what the universe has always done, remembering. Think about what memory means. It is not simply storage, it is recognition, the ability to identify the past within the present, to see continuity across time. When you remember a childhood afternoon, the neurons in your brain create a pattern similar to the one that existed when the memory was first formed. Memory is not retrieval, but reconstruction, a recreation of the past using the materials of the present. In this sense, memory is always a kind of echo, a reflection of something that once was, preserved imperfectly, but meaningfully, in a system capable of recognizing it. The universe has no brain, no neurons, no mechanism for thought, as we understand it, yet it preserves information with perfect fidelity. The light from a distant galaxy carries an image of that galaxy as it existed billions of years ago when the light first began its journey. The isotopes in a meteorite record the conditions of the early solar system. The pattern of galaxies in the cosmic web reflects the distribution of matter shortly after the Big Bang. The past is not gone, it is folded into the present, embedded in the structure and content of the universe, waiting to be read by those who know how to look. And perhaps that is what we are, the universe looking back at itself, capable of reading its own history, of translating light and matter into meaning. We are not separate observers watching the cosmos from outside. We are participants, expressions of the same processes that built galaxies and stars. The universe does not remember itself the way we remember yesterday. It remembers itself through us, through consciousness, through the capacity to ask questions and seek answers. But what if we only see what the universe allows itself to remember? What if there are chapters of cosmic history that left no trace, no echo, no fossil to decipher, silences in the story that we will never be able to fill? In the quantum realm, reality behaves in ways that defy every intuition we have built from living in the macroscopic world. A particle does not have a definite position and momentum simultaneously. An electron does not orbit an atom like a planet around a star, but exists as a cloud of probability, present everywhere and nowhere until the moment of measurement. This is not a limitation of our instruments, or a gap in our knowledge. It is a fundamental property of nature itself, encoded in what Werner Heisenberg called the uncertainty principle. Heisenberg discovered that the more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This is not because measurement disturbs the particle, but because position and momentum are complementary properties that cannot both be sharply defined at the same time. The universe, at its most fundamental level, is not made of things with definite properties, but of possibilities that crystallize into actuality only when observed. Before measurement, a particle exists in a superposition of states, occupying multiple positions or possessing multiple energies simultaneously. This seems absurd. How can something be in two places at once? How can reality be indeterminate, waiting for observation to decide what is real? Yet every experiment designed to test quantum mechanics has confirmed this strange behavior. Particles sent through a double-slit apparatus create an interference pattern as if each particle passes through both slits, simultaneously, existing as a wave of probability, but place a detector at one slit to see which path the particle takes, and the interference pattern vanishes. The act of observation collapses the wave function, forcing the particle to choose a single path. Niels Bohr, one of the architects of quantum theory, argued that we must abandon the idea of an objective reality existing independently of observation. The properties of particles, he suggested, do not exist until they are measured. Observation is not passive reception, but active participation in the creation of reality. This idea troubled even Einstein, who famously objected that God does not play dice with the universe. Yet the dice keep rolling, and quantum mechanics keeps predicting their outcomes with astonishing precision, even as it denies that the dice have definite faces before we look at them. If a particle can exist in multiple states simultaneously, what happens when those states are macroscopic, large enough to see and touch? Erwin Schrödinger posed this question through a thought experiment that has become one of the most famous paradoxes in physics. A cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, the vial breaks, and the cat dies. Quantum mechanics says the atom exists in a superposition of decayed and not decayed states until observed. Does this mean the cat is simultaneously alive and dead until someone opens the box? Schrödinger intended this as a critique, an illustration of the absurdity of applying quantum rules to everyday objects. Yet the paradox reveals a deep question: where is the boundary between the quantum world of superpositions and the classical world of definite outcomes? Why do we never observe superpositions at human scales? One answer is decoherence, the idea that interactions with the environment cause quantum superpositions to collapse almost instantly for large objects. A cat is not isolated like a particle in a laboratory vacuum. It is constantly interacting with air molecules, photons, and its own internal processes, all of which measure it, collapsing its wave function trillions of times per second. But decoherence does not fully solve the measurement problem. It explains why we do not see macroscopic superpositions, but not what happens during measurement itself, what transforms a wave of possibilities into a single outcome. Some physicists interpret the wave function as a description of our knowledge rather than physical reality. Measurement simply updates our information about the system. Others embrace the many worlds interpretation, suggesting that every quantum measurement causes the universe to split into parallel branches, each realizing a different outcome. In one branch, the cat lives, in another it dies. Both outcomes are real, but we only experience one. The universe, in this view, is not a single story but an infinite branching tree of stories, every possibility unfolding in some parallel reality. We perceive collapse not because the wave function actually collapses, but because our consciousness follows one branch while remaining blind to all the others. This interpretation preserves determinism. The wave function evolves smoothly without collapse, but at the cost of multiplying realities beyond measure. Every decision, every quantum event, every moment spawns countless universes. And if that is true, then reality is not observed but continually created, not singular but infinitely plural, not a wave that collapses but a wave that never stops expanding, carrying every possibility forward into existence. Perhaps consciousness is not separate from the physical world, but woven into its fabric, an emergent property of complex systems capable of self-reference. The brain is not a receiver tuning into consciousness from some external source, but a generator creating subjective experience from the electrochemical patterns of neural activity. Yet consciousness feels like more than mechanism. It feels like presence, awareness, the inexplicable fact of experience itself, what philosophers call qualia, the redness of red, the painfulness of pain, the subjective texture of being. Some physicists and philosophers have speculated that consciousness plays a fundamental role in quantum mechanics, that observation by a conscious mind is what collapses the wave function. This interpretation, associated with physicists like John von Neumann and later with more speculative theories, suggests that reality remains in potential until witnessed by awareness. But this raises more questions than it answers. What counts as conscious observation? Does a dog collapse wave functions? A bacterium? A sophisticated machine? And if consciousness is required for reality to crystallize, how did the universe exist for billions of years before conscious beings evolved? A more subtle idea is that the universe does not require external observers, but is itself a self-observing system. Quantum mechanics describes how systems interact and become entangled, how information propagates through space-time, how the act of one part of the universe measuring another creates correlations and defines outcomes. In this view, observation is not a special process requiring consciousness, but a fundamental feature of physical interaction. Every particle that collides with another, every photon that scatters off an atom, is an act of observation, a moment where possibility becomes actuality. The universe, then, has been observing itself since the beginning. Atoms measure each other, galaxies measure light, stars measure the pressure and temperature of their cores, and eventually, after billions of years of cosmic evolution, matter organized itself into systems complex enough to observe not just other systems but themselves, to become self-aware, to reflect on their own existence, to ask how observation works and what reality is. When the universe observes itself through us, it becomes conscious of its own nature, capable of formulating quantum mechanics and wondering about the role of consciousness in reality. We are not witnesses standing outside the cosmos, but mirrors in which the universe recognizes its own reflection. But if observation creates reality, or at least participates in defining it, then we are never neutral observers. Every measurement leaves a trace, every interaction alters what is observed, and even the questions we choose to ask shape the answers the universe provides. In quantum experiments, deciding whether to measure a particle's position or its momentum determines what kind of information we can extract. The two measurements are mutually exclusive, revealing complementary but incompatible aspects of reality. The universe does not present us with a complete picture. It shows us only what our methods of observation allow us to see. This is not a failure of science, but a fundamental feature of existence. Knowledge is always partial, always contextual, always shaped by the relationship between observer and observed. The shadow of the observer falls across every measurement, every theory, every attempt to grasp reality objectively. And perhaps this is not a limitation, but an invitation to recognize that we are not separate from the universe we study, that our questions and methods and consciousness are part of the cosmic story, not footnotes to it. What if we are not in the universe, passively receiving information about an external reality? What if the universe is within observation itself, an ongoing process of self-interaction, self-measurement, self-creation? What if reality is not a noun, but a verb, not a thing that exists but an action that happens, a continuous unfolding in which observation and observed are two aspects of a single process? Then the paradox dissolves. There is no gap between mind and matter, no mystery of how consciousness can affect the physical world, because consciousness is the physical world becoming aware of itself, and every observation is the universe looking into a mirror and seeing not something other than itself, but another facet of what it has always been. We experience time as a river, flowing from past through present into future, carrying us along, whether we wish to move or not. Memory gives us access to the past, but only as fading images, imperfect reconstructions. The future remains veiled, unknowable until it becomes present and then immediately slips into the past. This flow feels absolute, universal, the same for everyone everywhere. But Einstein revealed that time is not a river at all. It is a landscape, and different observers move through it at different rates depending on their motion and the gravitational fields they inhabit. His special theory of relativity, published in 1905, showed that time dilates for objects moving at high speeds. A clock on a fast-moving spaceship ticks more slowly than an identical clock at rest, not because of any mechanical defect, but because of the geometry of space-time itself. If you traveled at near light speed for what felt like 1 year and then returned to Earth, you might find that decades had passed for those who remained behind. Time, Einstein proved, is not a universal constant, but a relative phenomenon, different for different observers depending on their motion through space. But gravity, too, affects time. Einstein's general theory of relativity, completed in 1915, described gravity not as a force but as the curvature of space-time caused by mass and energy. A massive object like Earth bends the fabric of space-time around it, and this curvature affects how time flows. Clocks run more slowly in stronger gravitational fields, so a clock at sea level ticks slightly slower than one on a mountaintop. Near a black hole where gravity becomes extreme, time slows dramatically. An observer falling toward the event horizon would appear to an outside observer to freeze in time, never quite crossing the boundary, while from the falling observer's perspective, they would cross in finite time and be destroyed by tidal forces. This means that past, present, and future are not absolute categories that depend on reference frame. Events that are simultaneous for one observer occur in sequence, for another, moving relative to the first. The block universe model takes this seriously. If simultaneity is relative, then all moments in time are equally real, existing together like pages in a book. The flow of time is not a feature of the universe, but a feature of consciousness, a subjective experience of moving through a static four-dimensional space-time where past and future are as real as present, just located at different coordinates along the time axis. Consider a photon, a particle of light, emitted from a distant star and traveling through space for 1 billion years before entering your eye. From your perspective, that journey took vast stretches of time, crossing distances almost incomprehensible in scale. But from the photon's perspective, if we could imagine such a thing, no time passes at all. At the speed of light, time dilation becomes infinite. The photon's clock does not tick. For it, emission and absorption are the same moment. The universe, from light's point of view, is frozen, compressed into a single eternal instant. This is not metaphor, but consequence of the mathematics of relativity. As velocity approaches the speed of light, the time dilation factor approaches infinity, and lengths contract along the direction of motion. At exactly the speed of light, distance in the direction of travel shrinks to zero. A photon traveling from the Andromeda galaxy, 2.5 million light-years away, experiences no distance and no duration. It does not age, does not change, does not experience sequence or causality, or any of the temporal structures we take for granted. Light exists at the boundary between time and eternity, moving through space-time but not experiencing it, connecting distant events without ever occupying the duration between them. In a sense, every photon carries its origin with it. The moment of its emission remains present to it, because no time has elapsed. When you look at a star, the light entering your eye is billions of years old from your perspective, but eternally young from its own. You are seeing the past directly, without mediation, because light does not forget or age or transform. It simply is. And perhaps this tells us something profound about time itself, that it is not a substance or a medium, but a relationship, a structure that depends on motion and gravity and reference frame. That the flow we experience is not the universe moving forward, but our consciousness moving through a geometry where all moments exist simultaneously, like cities on a map. We can only visit one city at a time, but that does not mean the others vanish when we leave. They remain, fixed in the landscape of space-time, accessible to light, which moves through time without being subject to it. On Earth, the effects of time dilation are tiny, measurable only with atomic clocks precise enough to detect nanosecond differences. But those differences are real. GPS satellites, orbiting at high altitude and high speed, must account for both special relativistic time dilation, moving clocks run slow, and general relativistic time dilation. Clocks in weaker gravity run fast. Without corrections for relativity, GPS coordinates would drift by several kilometers per day. Your smartphone navigation depends on Einstein's equations, written a century before smartphones existed, to reconcile the different rates at which time flows for satellites and receive. Near massive objects, the warping of time becomes dramatic. A clock near the surface of a neutron star, an object with the mass of the Sun compressed into a sphere 20 kilometers wide, would tick noticeably slower than one in empty space. And near a black hole, time's flow changes so drastically that it reshapes our understanding of reality. The event horizon, the boundary from which not even light can escape, is a surface in space-time where time and space exchange roles. Outside the horizon, you can move freely through space, but are carried inexorably forward in time. Inside, you can move freely through time, but are carried inexorably toward the singularity. Einstein's field equations relate the curvature of space-time to the distribution of mass and energy through a simple but profound statement. Space-time tells matter how to move, and matter tells space-time how to curve. This feedback loop is what we call gravity, not a force pulling objects together, but a geometry that channels their motion. A planet orbits a star not because the star exerts a force across empty space, but because the star's mass curves space-time, and the planet follows the straightest possible path, a geodesic through that curved geometry. What looks like orbital motion from outside is actually straight line motion through warped space. This is why gravity affects time. Time is not separate from space, but woven with it into space-time, and when mass curves space, it also curves time. The deeper you descend into a gravitational well, the more slowly your clock ticks relative to clocks farther away. You age more slowly, chemical reactions proceed more slowly, thoughts unfold more slowly. Yet from your own perspective, nothing changes. You remain the reference frame against which you measure duration. It is only when you compare your clock to one at a different gravitational potential that the difference reveals itself, showing that time is not a universal backdrop, but a local phenomenon, shaped by the matter and energy that surround it. At the event horizon of a black hole, time dilation becomes infinite. A distant observer watching someone fall toward a black hole would see them slow down asymptotically, their image dimming and redshifting, as light struggles to escape the intensifying gravitational pull. The falling person would appear to freeze at the horizon, never quite crossing it, suspended eternally at the boundary between escape and capture. But from the perspective of the one falling, they would cross the horizon in finite proper time, experiencing nothing unusual at the moment of crossing, just continued free fall toward the singularity at the center. This asymmetry reveals something fundamental about time. It is not a single unified flow, but a network of interwoven flows, different for different observers, all equally valid, none privileged. The block universe does not mean time is an illusion, but that its structure is richer and stranger than we assumed. Past and future are not non-existent, but elsewhere, located at different coordinates in space-time, accessible in principle but not always in practice. The horizon of a black hole marks a boundary not just in space but in time, a threshold beyond which the future of one observer becomes causally disconnected from the past of another. And what of the singularity itself, the point at the center where space-time curvature becomes infinite and general relativity breaks down? Is it a place where time ends, where the smooth geometry of Einstein's equations tears apart into quantum foam, or is it a doorway to something stranger, a white hole expelling matter into another universe, a wormhole connecting distant points in space-time, a seed of a new cosmos? We do not know. Singularities are where our theories reach their limits, where the equations produce infinities and lose predictive power, where quantum mechanics must somehow merge with general relativity to describe what actually happens. But perhaps the deepest mystery is not what occurs at singularities, but what time itself is in the absence of change. If time is the measurement of change, the relationship between events, the structure that allows causality to operate, then what is time in a universe that has reached thermodynamic equilibrium, where entropy has maximized and nothing more can happen? What if eternity is not infinite duration but timeless presence, a state where past and future collapse into an eternal now, because there is no change to distinguish one moment from another? Then time would not end but dissolve, not cease but become meaningless, and the universe would exist forever in a single frozen instant, like light eternal, motionless, complete. Edwin Hubble's discovery that galaxies are receding from us, and that more distant galaxies recede faster, revealed the universe's expansion. But for decades, astronomers assumed that expansion must be slowing, decelerated by the gravitational pull of all the matter in the universe. The question was not whether expansion would eventually halt and reverse, leading to a big crunch, but when, yet in the late 1990s, two independent teams, studying distant supernovae, exploding stars that serve as cosmic distance markers, made a startling discovery: the expansion is not slowing down, it is accelerating. This should not be possible. Gravity is attractive, matter pulls on other matter, slowing expansion. For the universe to accelerate, something must be pushing outward, counteracting gravity, and this something must dominate the energy budget of the cosmos. Astronomers named it dark energy, not because it is dark like dark matter, but because it is completely unknown. It does not emit light, does not absorb light, does not cluster like matter. It appears to be a property of space itself, a uniform energy density that remains constant as the universe expands, so that as space grows, the total amount of dark energy increases. The simplest explanation is Einstein's cosmological constant, a term he added to his field equations in 1917 to allow for a static universe balancing gravitational attraction with a repulsive force. When Hubble discovered expansion, Einstein reportedly called the cosmological constant his biggest blunder and removed it. But the constant reappeared decades later, resurrected by observations showing that empty space has energy. Quantum field theory predicts that even a vacuum is not truly empty, but seethes with virtual particles and fluctuating fields, and this quantum foam should contribute energy density to the universe. The problem is that calculations predict a vacuum energy 20 orders of magnitude larger than observed, the largest discrepancy between theory and experiment in all of physics. So we do not know what dark energy is, only what it does. It drives the universe's accelerating expansion, stretching space itself at an ever-increasing rate. Galaxies beyond our local cluster are receding faster than light, not because they move through space, but because space between us and them grows faster than light can cross it. Eventually, in trillions of years, every galaxy outside our own local group will disappear beyond a cosmic horizon, their light redshifted to infinite wavelengths, leaving our descendants in a universe of profound darkness, with no evidence that other galaxies ever existed. What does it mean for empty space to have energy? In classical physics, a vacuum is simply the absence of matter and fields, a state with zero energy, but quantum mechanics forbids absolute emptiness. The uncertainty principle implies that energy fluctuates even in a vacuum, with particle-antiparticle pairs constantly appearing and annihilating in timescales so brief they cannot be directly observed. These virtual particles are not merely mathematical artifacts but have measurable effects, such as the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force, because the space between them excludes certain wavelengths of virtual particles, creating a pressure difference. If vacuum energy exists, it should contribute to space-time curvature, acting as a kind of anti-gravity that pushes space apart rather than pulling it together. The cosmological constant in Einstein's equations can be interpreted as exactly this: a uniform energy density, filling all of space, unchanging as the universe expands, exerting negative pressure that drives acceleration. But why is its value so small? Why does it dominate the universe's energy budget only recently, after billions of years during which matter and radiation were the primary components? These questions remain among the deepest unsolved problems in cosmology and physics. Some physicists speculate that dark energy is not a cosmological constant, but a dynamic field, varying in space and time, called quintessence. Others propose modifications to general relativity itself, suggesting that gravity behaves differently on cosmic scales than Einstein predicted. Still others invoke the anthropic principle. If dark energy were much larger, the universe would have expanded too rapidly for galaxies and stars to form, and we would not exist to observe it. Perhaps we live in a universe finely tuned for complexity, not by design, but by selection. One bubble in a vast multiverse where different regions have different physical constants, and only those with values compatible with life develop observers to wonder why the constants have the values they do. Nothing, it turns out, is the most powerful force in the universe. Not the nothing of absence, but the nothing of potential, the quantum vacuum that underlies all fields, all particles, all space-time. It is the canvas on which reality is painted, and it is not passive but active, contributing energy, shaping expansion, determining the ultimate fate of the cosmos. And perhaps this is fitting. If the universe began from nothing, or from something indistinguishable from nothing, then it makes sense that nothing remains the substrate, the foundation, the source from which everything emerges, and to which everything might one day return. Dark energy does not pull or push in the way forces do. It does not exert pressure on objects or accelerate particles. It is not mediated by any known particle or field in the way electromagnetism is mediated by photons or gravity, by the curvature of space-time, yet it shapes the universe's expansion, determining not just the rate at which space grows, but the ultimate geometry and fate of the cosmos. It is an architect without blueprint, a force without intention, a driver of cosmic evolution that operates through the simplest possible mechanism, being everywhere, uniformly, unchangingly. This uniformity is strange. Matter clumps into galaxies and clusters. Radiation disperses and dilutes as the universe expands, but dark energy remains constant in density. So as space grows, the total amount of dark energy increases. It is as if every cubic meter of space carries with it a fixed quantum of energy, and creating more space creates more energy, without violating conservation laws, because space itself is dynamic, part of the evolving geometry of the universe. This property, constant density despite expansion, makes dark energy fundamentally different from matter or radiation, neither of which can maintain constant density as the universe grows. If dark energy dominates forever, the universe will continue accelerating, becoming colder, emptier, darker. Stars will exhaust their fuel and fade. Galaxies will drift apart beyond each other's cosmic horizons. Eventually, even protons might decay, atoms dissolving into radiation. The universe would approach a state of maximum entropy, a heat death where no energy gradients remain to drive any process. No differences exist to mark the passage of time. Yet even this end state would not be nothingness. Space would still exist, still expand, still carry its vacuum energy, a dim glow of quantum fluctuations in an otherwise perfectly uniform darkness. Or perhaps dark energy will change. Perhaps it is not a constant, but a field evolving towards some future state. Perhaps its strength will increase, tearing apart galaxies, then stars, then atoms, in a big rip, where the fabric of space itself is destroyed. Or perhaps it will decrease, allowing gravity to reassert control, halting expansion, pulling the universe back into a big crunch, a fiery collapse into a singularity that might spark another Big Bang, We do not know. The invisible architect has not revealed its full design, and we are left to infer its intentions from the motions of galaxies, the light of distant supernovae, the whispers of a cosmos whose deepest workings remain hidden. Stand outside on a clear night, far from city lights, and look up. The stars you see are all part of our galaxy, the Milky Way, a collection of hundreds of billions of suns bound together by gravity into a rotating disk. Between the stars, space. Between the galaxies, more space, and that space is not passive backdrop, but active participant, expanding, creating distance where none existed, pushing galaxies apart, not by moving them through space, but by growing the space between them. The breath between galaxies is not inhalation or exhalation, but continuous expansion, a slow, relentless stretching that never ends. Dark energy drives this breath, invisible, uniform, pervasive. It does not interact with matter, except through gravity, or rather through its effect on the geometry of space-time. It does not clump or flow or radiate. It simply is a baseline energy of existence, the ground state of the cosmos, and in being so simple, so uniform, it might be telling us something fundamental about the nature of reality, that existence itself has energy, that space is not merely a container for fields and particles, but a field in its own right, capable of dynamics and evolution. What if the true force of creation is not motion, but stillness expanding? Not the violent explosion of the Big Bang, but the quiet, persistent growth of space itself, carrying matter and light along like leaves on a river whose current is the stretching of distance. What if the universe's most profound act is not complexity or life or consciousness, but simply the ongoing affirmation of its own existence, the insistence on being rather than not being, manifested as the expansion of space, the unfolding of time, the persistence of energy, even in the emptiest regions of the cosmos? Then dark energy is not mysterious, but essential, not an anomaly, but the signature of existence itself. And the breath between galaxies is the breath of the universe, inhaling possibility from the quantum vacuum, exhaling reality into space-time, continuing the process. It began 13.8 billion years ago, and might continue for trillions more, until perhaps the breath ceases, or transforms, or reveals itself to have been something other than breath. All along, a pulse, a wave, a cycle that ends only to begin again. In the human brain, there exist neurons that fire both when we perform an action and when we observe someone else performing that same action. These mirror neurons allow us to understand others not through abstract reasoning, but through internal simulation, as if we are performing their actions ourselves. They are the biological basis of empathy, imitation, learning, the mechanism by which consciousness recognizes itself in another. But what if this mirroring extends beyond biology? What if the universe itself operates through a similar principle of self-recognition, each part reflecting and responding to every other part? Quantum mechanics suggests something like this through entanglement, the phenomenon where particles that have interacted remain correlated no matter how far apart they travel. Measure the spin of one entangled particle, and you instantly know the spin of its partner, even if it is on the other side of the galaxy. Einstein called this spooky action at a distance, but it is not action. No signal travels between the particles. Instead, they share a single quantum state, a unified description that cannot be decomposed into separate properties for each particle. They are not two things, but one thing extended across space, a correlation written into the fabric of reality itself. Roger Penrose has speculated that consciousness might arise from quantum processes in the brain, specifically in structures called microtubules within neurons. If true, consciousness would not be merely electrochemical, but quantum mechanical, involving coherence and superposition at scales larger than individual particles. This remains highly controversial and unproven, but it raises a tantalizing question. If consciousness involves quantum processes, and quantum processes exhibit entanglement and non-locality, then might consciousness be fundamentally connected to the structure of space-time itself? Perhaps mind and matter are not separate categories, but different aspects of a single underlying reality. Matter organizes itself into patterns, atoms into molecules, molecules into cells, cells into brains, and at sufficient complexity, these patterns become self-aware. The universe, through billions of years of evolution, has created structures capable of reflecting on their own existence, of asking how they came to be, and what they are made of. In this sense, consciousness is the cosmos becoming aware of itself, the mirror through which reality sees its own face. When you think about the universe, you are the universe thinking about itself. This is not metaphor but literal fact. The atoms in your brain were forged in stars. The energy powering your thoughts comes from food made by photosynthesis, a process driven by sunlight created by nuclear fusion energy that originated in the Big Bang. Every thought you have is a cosmic event, a reorganization of matter and energy that extends the process of creation into the present moment. Consciousness is recursion, the ability of a system to take itself as its own object of contemplation. A thermostat senses temperature and adjusts its behavior, but it does not know it is sensing. A computer processes information according to algorithms, but it does not experience processing. Humans and perhaps other animals to varying degrees not only sense and process, but are aware that they sense and process. We think, and we know that we think. We observe our own observations. We are systems that have become self-referential, capable of examining not just the external world, but the internal mechanisms by which we examine it. This recursion might be the defining feature of consciousness. When the brain creates a model of the external world, constructing a three-dimensional representation from two-dimensional retinal images, predicting the trajectories of moving objects, inferring the mental states of other people, it also creates a model of itself as an agent within that world. The self is not a thing, but a process, a continuously updated narrative that integrates sensory input, memory, and prediction into a coherent story of a being moving through time. And this story is told by the brain to itself, a loop of self-reference that gives rise to the feeling of being someone, of having a perspective, of existing as a subject rather than merely an object. If consciousness is self-reference, then perhaps the universe has always been dimly conscious, capable of responding to itself through physical laws. Particles interact according to forces and fields. This is the universe measuring itself, updating its state based on its own structure. But only when matter organized into brains did the universe become capable of explicit self-reference, of formulating theories about its own nature, of experiencing wonder and curiosity about its origins. We are not observers standing outside the cosmos, but the means by which the cosmos becomes self-aware, the eyes through which it sees itself. Some interpretations of quantum mechanics suggest that reality is fundamentally informational rather than material. John Wheeler, one of the great physicists of the 20th century, proposed that the universe is participatory, that observation is not passive, but creative, and that information, not matter or energy, is the primary substance of existence. He coined the phrase, "it from bit," suggesting that every physical thing derives ultimately from yes or no questions, from binary choices, from bits of information encoded in the quantum states of particles and fields. If reality is information, then what is the universe? A vast computation, perhaps, running on the substrate of quantum fields, processing information through every particle interaction, every collapse of a wave function, every entanglement and decoherence. This leads to the simulation hypothesis, the idea that our entire universe might be a computer simulation run by a more advanced civilization, and that we are conscious subroutines within that simulation, unaware of the computational substrate on which we run. This idea, popularized by philosophers like Nick Bostrom, is both fascinating and unfalsifiable. If we are in a simulation, and the simulation is complete enough to include physics, chemistry, biology, and consciousness, then there is no experiment we could perform to detect the simulation from within. Any anomaly or glitch we discovered would simply be a feature of the simulated physics, not evidence of computation. The hypothesis cannot be disproven, which means it cannot be tested, which means it is not science, but metaphysics, a modern version of ancient questions about the nature of reality and whether the world we perceive is ultimately real or illusory. But even if we are not in a simulation, the informational view of reality suggests something profound, that the universe might be, in some sense, dreaming itself into existence. Dreams are constructed by the brain from memory, emotion, and random neural activity, woven into narratives that feel real while we experience them. What if the universe constructs reality in a similar way, not from neural activity, but from quantum processes, from the interplay of waves and particles, fields and forces? What if matter is the dream and consciousness is the dreamer, not separate entities, but two aspects of a single process, existence becoming aware of itself, possibility collapsing into actuality, the universe waking up from the long sleep of non-existence? The hard problem of consciousness, so philosopher David Chalmers calls it, is explaining why and how physical processes in the brain give rise to subjective experience. We can map neural correlates of consciousness, identify which brain regions are active during particular experiences, trace the flow of information through neural networks. But none of this explains why these processes feel like something, why there is an inner life, why the lights are on inside our heads. Neuroscience can describe the mechanisms of perception and cognition, but it cannot yet explain experience itself. Perhaps this is because we have the relationship backward. We assume matter is primary and consciousness is derived, an emergent property that appears when matter is organized in sufficiently complex ways. But what if consciousness is fundamental and matter is the emergent property? This is the view of panpsychism, the ancient philosophical position now being reconsidered by some scientists and philosophers. If consciousness is a basic feature of reality, present in some form at all levels of organization, then the hard problem dissolves. Consciousness does not emerge from unconscious matter. It is an intrinsic aspect of what matter is. This does not mean electrons have thoughts or atoms have emotions, but that some primitive form of experience, perhaps simple responsiveness, a proto-awareness, is present in all physical systems, and what we call consciousness is what this fundamental property becomes when organized into complex structures like brains. The universe would then be not dead matter governed by blind laws, but a vast tapestry of experience, most of it unimaginably simple, but in some places like human brains, organized into rich, reflective, self-aware consciousness. What if thought and space-time share the same origin? What if the patterns of neural activity that constitute your thoughts are not fundamentally different from the patterns of quantum fields that constitute space-time, matter, and energy? What if both are information, structured in different ways but arising from the same underlying reality? Then the gap between mind and matter would not be a chasm to be bridged, but an illusion created by viewing a single phenomenon from two different perspectives. We are not minds trapped in matter. We are matter that has learned to reflect on itself, space-time that has organized into thought, the universe recognizing its own existence through the only means available by becoming conscious. Carl Sagan famously said, "We are made of star stuff," and it is true in the most literal sense. Every atom of carbon in your body was created in the core of a dying star through the fusion of helium nuclei. Every atom of oxygen was forged in stellar furnaces where temperatures reached billions of degrees. The iron in your blood was synthesized in the final moments of a supernova explosion, that catastrophic death of a massive star that scattered its enriched contents across light years of space. You are not merely on the Earth, but of it. And the Earth is not separate from the cosmos, but a condensation of matter that has traveled for billions of years through the universe. The calcium in your bones, the phosphorus in your DNA, the nitrogen in your proteins, all of these elements were created in stars, Sometimes through multiple generations of stellar life cycles, the first stars formed from pure hydrogen and helium, left over from the Big Bang, had no heavy elements to build planets or life. They lived and died, enriching the cosmos with carbon, oxygen, silicon, iron. Second-generation stars formed from these enriched clouds, and around some of them, planets condensed. On at least one of those planets, the elements organized into molecules, molecules into cells, cells into organisms capable of replication, evolution, thought. This is your lineage. You are descended not just from ancestors who walked on two legs and painted caves, but from stars that burned for millions of years and then exploded, from clouds of gas that collapsed under gravity, from the quantum fluctuations in the first seconds of the universe that seeded the formation of all structure. Your body is a temporary arrangement of ancient atoms, borrowed from the Earth and the cosmos, on loan for a few decades before they return to the cycle of matter, scattered into soil, air, water, eventually back into space, perhaps one day into new stars and planets. And your memories, too, are stardust. The neural patterns that encode your experiences are written in the configurations of molecules, in the strengths of synaptic connections, in the electrical and chemical activity of a brain made of elements forged in stellar cores. When you remember a moment from childhood, you are activating a pattern of atoms that once existed in a star's heart, now organized into the most complex structure we know of in the universe, a structure capable of preserving the past and projecting it into consciousness. Human life, measured against cosmic time, is almost absurdly brief. The universe is 13.8 billion years old. The sun has been burning for 4.6 billion years and will continue for another 5 billion. Earth has hosted life for at least 3.5 billion years, with complex multicellular organisms appearing in the last 600 million, dinosaurs ruling for 55 million, and Homo sapiens emerging only 300,000 years ago. An average human lifespan of 80 years is 6/10 millionths of the universe's age, a flicker so brief that if cosmic history were compressed into a single year, all of human civilization would occupy the last few seconds before midnight on December. And yet, within that flicker, we have deciphered the age of the universe, mapped the cosmic microwave background, detected gravitational waves from colliding black holes billions of light years away, understood the nuclear processes that power stars, traced our evolutionary lineage back to single-celled organisms, and begun to ask what consciousness is and whether we are alone in the cosmos. Our brevity does not diminish our significance, it amplifies it. We are ephemeral structures capable of comprehending eternity, temporary patterns of matter, capable of understanding the laws that govern all matter everywhere. This fragility is not a flaw, but a necessity. Complex structures like living organisms exist far from thermodynamic equilibrium, maintaining their organization by consuming energy and exporting entropy to their surroundings. We are dissipative structures, temporary islands of order, in a universe trending toward disorder, maintained by the continuous flow of energy from the sun through the biosphere and ultimately radiated into space as waste heat. We cannot last forever, because forever is not compatible with complexity. Only simple, low-entropy states can persist indefinitely. To be complex, adaptive, conscious, to be alive, is to be temporary. But temporary does not mean meaningless. In the cosmic window of our existence, we are the universe's way of knowing itself, of experiencing beauty and wonder, of asking questions and seeking answers. We are fragile observers, yes, but we are observers nonetheless, capable of looking backward across billions of years to the origin of space-time and forward across trillions of years to the ultimate fate of the cosmos. Our lifespan is brief, but our perspective is vast, and in that vastness, we touch something eternal. It is humbling to recognize how small we are. Earth is a pale blue dot, as Voyager's camera showed us from the edge of the solar system, a mote of dust suspended in a sunbeam, as Carl Sagan described it. Our planet orbits an average star in the outer reaches of an ordinary spiral galaxy, one of hundreds of billions of galaxies in the observable universe. The distances are so vast that light, traveling at 300,000 kilometers per second, takes over 100,000 years to cross our galaxy and billions of years to reach us from the most distant objects we can observe. We are small in space and small in time, occupying a minuscule fraction of the cosmos in every dimension, and yet smallness is not insignificance. To be small is to be particular, to be specific, to be an individual instance, rather than an abstract general principle. The universe is vast, but vastness alone produces nothing interesting. It is in the details, the precise arrangement of atoms in a DNA molecule, the specific pattern of neural connections in a brain, the unique history of a planet's geology and climate, that complexity and meaning arise. Scale is perspective. From the viewpoint of a galaxy, Earth is invisible, irrelevant, less than a speck. But from the viewpoint of a human, Earth is everything, the source of life, the stage of history, the only home we have ever known. Both perspectives are valid, neither more true than the other. The universe does not have a preferred scale. Physics operates at all levels, from quantum foam to superclusters, and no level is more fundamental or important than any other. To be small is not to be less real or less valuable. It is simply to occupy one scale among many, and perhaps there is comfort in smallness. To be small is to belong to something larger, to be part of a structure that extends beyond yourself in space and time. You are not separate from the universe, but embedded within it, connected to every other part through chains of causality and shared origin. To be small is to be humble, to recognize that you are not the center of existence, but one expression of it among countless others. And in that humility lies a kind of peace, the peace of knowing that you do not have to carry the weight of cosmic significance alone, that you are one note in a symphony that has been playing for billions of years and will continue long after you are gone. Every breath you take connects you to the history of life on Earth. The oxygen molecules entering your lungs were produced by photosynthesis, split from water molecules by plants and algae using energy from sunlight. Some of those oxygen atoms might have been breathed by dinosaurs, by ancient humans, by trees that grew and died millennia ago. The carbon dioxide you exhale will be absorbed by plants, incorporated into sugars, released again by respiration or decay, cycling through the biosphere in an endless exchange. This exchange, respiration, photosynthesis, the carbon and oxygen cycles, is a planetary scale process, linking every living thing into a single interconnected system. The biosphere is not a collection of isolated organisms, but a unified whole, maintained by the flow of energy from the sun and the cycling of matter through ecosystems. You are not a separate entity, but a participant in this flow, a temporary eddy in the river of life that has been flowing on Earth for billions of years. And the breath extends beyond Earth. The oxygen you breathe was created in stars. The water molecule split by photosynthesis contains hydrogen from the Big Bang and oxygen from stellar nucleosynthesis. The energy powering photosynthesis comes from the sun's nuclear fusion, converting mass into energy according to Einstein's equation. The fusion itself is possible because of quantum tunneling, a phenomenon where particles pass through energy barriers that classical physics says should be impenetrable. Everything connects, quantum mechanics to nuclear physics, to stellar evolution, to planetary chemistry, to biology, to consciousness. Perhaps to live is to continue the expansion in miniature, to take the energy and matter given to you by the universe and organize it into complexity, structure, meaning. You are a local reversal of entropy, a brief flourishing of order in a cosmos trending toward disorder, made possible only by the continuous flow of energy through your body. And when that flow ceases, when your breath stops and your atoms return to the world, you do not vanish, you transform, becoming part of the cycle that continues, your matter recycled, your energy redistributed, your existence rejoining the vast process from which it temporarily emerged. The breath that connects all things never ends, it only changes form. The second law of thermodynamics states that entropy, roughly disorder or randomness, always increases in a closed system. The universe appears to be a closed system, expanding but not exchanging energy with anything outside itself. This means that over time, energy gradients flatten, temperatures equalize, and useful work becomes impossible. Stars will exhaust their fuel and fade into white dwarfs, neutron stars, or black holes. Galaxies will drift apart beyond each other's cosmic horizons. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that causes them to slowly lose mass over timescales vastly longer than the current age of the universe. In this far future, sometimes called the heat death or big freeze, the universe would reach thermodynamic equilibrium, maximum entropy, uniform temperature just above absolute zero, no structure, no complexity, no life. Nothing would happen, because nothing could happen. There would be no energy gradients to drive processes, no differences to mark change, no time in any meaningful sense because time is the dimension along which change occurs. The cosmos would exist in a state of frozen uniformity, not dead because death implies a prior life, but simply still, unchanging, a vast dark expanse of dilute radiation and widely separated elementary particles. This fate assumes that dark energy remains constant and that the expansion continues accelerating forever. But we do not know if this assumption is correct. Dark energy might change, might decay into something else, might trigger new physics we have not yet imagined. The universe has surprised us before. The discovery of acceleration itself was unexpected. Perhaps there are surprises still to come, phenomena that will reshape our understanding of cosmic destiny. But even if heat death is inevitable, it lies trillions upon trillions of years in the future, a span of time so immense that all of recorded human history is less than a nanosecond in comparison. The stars will shine for trillions more years. New stars will form from remaining gas clouds for perhaps another 100 trillion years. Life, intelligence, civilization, these could persist and evolve in ways we cannot imagine across timescales that dwarf the current age of the universe. The death of the cosmos is not imminent. It is the final chapter of a story still early in its telling. Yet, what if the end is not final? Some cosmological models suggest that the universe might be cyclic, undergoing endless sequences of expansion and contraction, each Big Bang followed billions of years later by a big crunch, which ignites another Big Bang. In this oscillating universe model, the cosmos has no true beginning or end but exists in an eternal cycle, dying and being reborn infinitely. Each cycle might be similar to the last, or conditions might vary: different physical constants, different amounts of matter and energy, different outcomes. Loop quantum cosmology, a theoretical framework that attempts to merge quantum mechanics with general relativity, suggests that the singularity at the beginning of the Big Bang might be avoided through quantum effects. Instead of collapsing to infinite density, the universe might bounce at some maximum density, transitioning from a previous contracting phase to the current expanding phase. If true, our Big Bang was not the origin of existence, but a transition point, and before our universe there was another, and before that another, stretching backward without beginning. Stephen Hawking and Roger Penrose explored whether the universe could recollapse and whether time could be cyclic. Hawking's no-boundary proposal suggests that time might be finite, but unbounded, like the surface of a sphere, traveling far enough in one direction, brings you back to your starting point. In this model, asking what happened before the Big Bang is like asking what lies south of the South Pole. There is no before because time itself is a closed loop, and the universe is self-contained, requiring no external cause or creator. These models are speculative, constrained by mathematics, but not yet confirmed by observation. They offer alternatives to the linear narrative of a universe that begins in a Big Bang and ends in heat, death, or a big rip. They suggest that creation might not be a singular event, but an ongoing process, that endings might be beginnings, that the cosmos might have a memory extending beyond any single iteration. The possibility of return, whether through cycles, bounces, or some other mechanism we have not yet conceived, means the universe might be far older, stranger, and more resilient than our current models suggest. If the universe is cyclic, does each cycle remember the previous one? Probably not in any literal sense. A big crunch would destroy all structure, galaxies, stars, atoms, compressing everything back into a singularity or near singularity. Where the laws of physics break down, information would be erased, entropy reset, and the next cycle would begin without knowledge of what came before. Each universe would be like a new dream, emerging fresh from the quantum foam, with its own initial conditions, its own history, its own fate. Yet some physicists have speculated about loopholes. Perhaps information is not destroyed, but encoded in subtle ways in the values of physical constants, in the patterns of quantum fluctuations, in structures that survive the transition between cycles. Roger Penrose has proposed a model called conformal cyclic cosmology, in which the end of one universe becomes the beginning of the next, and certain information, specifically the distribution of mass energy at the end of one aeon, influences the initial conditions of the next. In this view, the universe does have a memory, written not in matter or light, but in the geometry of space-time itself. This is philosophy verging into metaphysics, ideas that stretch the boundaries of testability, but they touch on something profound: the human desire to believe that existence is not random or arbitrary, that there is continuity and meaning even in the face of cosmic endings. If the universe cycles eternally, then existence itself is eternal, taking different forms but never ceasing, never vanishing into absolute nothingness. Each cycle would be a repetition, yet also unique, like variations on a theme, the universe relearning itself, recreating its own patterns, perhaps approaching some form of perfection or completeness through endless iteration. Or perhaps eternity is not repetition, but transformation, each cycle fundamentally different from the last, the universe exploring the space of possible physical laws and initial conditions, trying every variation, every permutation, across a meta-time that transcends individual cosmic histories. Then we would be inhabitants of one realization among infinitely many, our universe just one note in an eternal symphony of creation, destruction, and rebirth. And the memory of eternity would not be stored anywhere but would be eternity itself. The fact that existence never ends, only changes, endlessly creative, endlessly renewing. Imagine the last star fading, its fuel exhausted, collapsing into a cold, dark remnant. Imagine the last black hole evaporating, its mass converted to radiation that disperses into the expanding void. Imagine the universe growing so vast, so empty, so cold that nothing remains, but widely separated particles drifting through darkness, no longer interacting, no longer forming structures, no longer capable of supporting anything we would recognize as complexity or life. This is the end, heat, death, the final equilibrium from which nothing new can emerge. But even in that end, energy exists. Space-time exists. Quantum fields exist, their ground states humming with zero-point energy. Virtual particles flickering in and out of existence, even in the deepest vacuum. And if the universe emerged once from quantum fluctuations, could it not emerge again? If the Big Bang was a spontaneous event, the quantum tunneling from one state to another, then perhaps in the infinite expanse of a dead universe, another such event could occur, a random fluctuation, creating a new Big Bang, a new space-time, a new universe erupting from the void. This would not be cyclical in the sense of a continuous process, but probabilistic, random, rare, but not impossible. In the vast stretches of time available in a heat-death universe, even incredibly improbable events become inevitable. And if our universe arose this way, spontaneously from nothing or from a previous state, then it might happen again and again, endlessly, each new universe existing in isolation from the others, separated by unimaginable gulfs of space and time, each with its own Big Bang, its own evolution, its own eventual silence. What if creation is not a start, but a breath that never stopped? What if the universe or the multiverse, the totality of all possible universes, is engaged in an eternal process of creation and dissolution, emerging and fading, being born and dying, not following a plan, but exploring the space of possibilities through trial and chance? Then the end is always also a beginning, and the beginning is always the continuation of something deeper, something that transcends any individual universe. We live in one breath among countless others, one moment in an eternal rhythm, one expression of existence's refusal to remain nothing, and perhaps that is enough to know that we are part of a process that never truly ends, only changes form, endlessly creative, endlessly present, endlessly itself. In the deep future, long after the last stars have burned out and the universe has expanded into cold darkness, there will still be light, not the light of stars or galaxies, but the faint afterglow of black holes evaporating through Hawking radiation, the soft glow of cosmic background radiation, redshifted to wavelengths longer than galaxies, the occasional flicker of virtual particles emerging from the quantum vacuum. Light does not cease. It only becomes rarer, dimmer, stretched by expansion into wavelengths so long they are barely distinguishable from the emptiness through which they travel. Imagine a photon, created in the last stages of a black hole's evaporation, traveling through a universe that has grown unimaginably vast and empty. There are no more galaxies to pass, no more stars to illuminate, no more planets on which observers might detect its passage. It travels alone through darkness, carrying energy but encountering nothing, a solitary messenger from a time when the universe still harbored structure and warmth. Eventually, after timescales beyond comprehension, even this photon will be stretched by expansion to wavelengths approaching infinity, its energy diluted to near zero, indistinguishable from the vacuum itself. This is the fading light, not extinguished but dispersed, not destroyed but transformed into something so diffuse and cold that it no longer interacts, no longer transfers energy, no longer participates in the processes we call physics. The universe does not go dark suddenly, like a switched-off lamp, but gradually, asymptotically, approaching but never quite reaching absolute emptiness. There is always something left: radiation, vacuum fluctuations, the faint echo of existence, but so little that nothing can happen, no complexity can arise, no information can be processed or stored. And yet, in this fading, there is a kind of peace. The universe, having exhausted its initial conditions, having explored all the structures and forms that gravity and quantum mechanics allow, settles into stillness. Not death, but rest. Not an end, but a pause perhaps before something new begins, or perhaps simply the final state, the destination toward which everything has been moving since the first moment. The silence that existed before sound and will exist after sound has faded away. Energy cannot be created or destroyed, only transformed. This is the first law of thermodynamics, one of the most fundamental principles in physics. Even in the heat death of the universe, energy does not vanish. It spreads out, becomes uniform, loses the gradients necessary to drive change, but it persists. The total energy of a closed system remains constant, even as the system evolves from order to disorder, from useful work to waste heat, from stars and galaxies to cold radiation and isolated particles. So what remains when all ends? Energy, dispersed but conserved. Space-time, still existing, still obeying Einstein's equations, still carrying whatever quantum fields underlie physical reality. The laws of physics themselves, mathematical relationships that govern how things behave, remain true even when there is almost nothing left to behave. The universe does not cease to exist. It simply reaches a state where nothing interesting happens anymore, where all processes have run their course, and there are no more gradients, no more differences, no more change, but existence itself remains. This is not nothing. Even an empty, cold, uniform universe is something, a space-time with geometry, with dimensions, with the potential for quantum fluctuations, and in that potential lies the possibility, however remote, that something new could emerge. If the Big Bang was a quantum event, a fluctuation from a false vacuum to a true vacuum or vice versa, then perhaps another such event could occur spontaneously in the far future, creating a new universe, a new Big Bang, a new cycle of creation. Existence, it seems, is more fundamental than any particular arrangement of matter or energy. The universe can change radically from hot, dense plasma to cold, sparse vacuum, while still existing, still being something rather than nothing. What remains when all ends is existence itself, stripped of structure and complexity, reduced to its most basic form, but still real, still present, still governed by the laws that have always governed it. And perhaps that is the deepest truth, that being is more fundamental than becoming, that existence precedes form, that the universe cannot not be, even when it is almost empty. We began this journey in silence, the silence before sound, before time, before the universe spoke itself into existence, and we return to silence now, at the end of all endings, when the last light has faded and the cosmos has settled into stillness. But the silence at the end is not the same as the silence at the beginning. The first silence was pure potential, pregnant with possibility, the quantum foam from which space-time and matter emerged. The final silence is actualized potential, the result of 13.8 billion years or more of cosmic evolution, the state toward which the second law of thermodynamics has been pushing since the first moment. Yet even in this final silence, there is memory. Not memory as we know it, neurons firing, synapses strengthening, patterns recalled, but memory in the structure of space-time itself. The universe has expanded from a singularity to an almost infinite expanse. That expansion is a record of its history, the geometric expression of time's passage, the distribution of matter and energy, however sparse, however cold, still reflects the initial conditions set at the Big Bang, the quantum fluctuations amplified by inflation, the gravitational clustering that built galaxies and stars. The past is not erased, but encoded, folded into the present configuration of the cosmos. This is the memory of silence, that the universe has been something, has done something, has evolved through countless transformations, and that these transformations are not lost, but embedded in the final state, like the rings of a tree recording years of growth, like sedimentary layers preserving ancient climates. The universe carries within it the story of its own becoming, and even if no observer exists to read that story, even if consciousness has long since vanished, and no mind remains to remember, the story is still there, written in the curvature of space-time, in the wavelength of the last photons, in the quantum states of the fields that fill the void. Before sound, there was silence. After sound, silence returns. But between those two silences was everything matter and energy, stars and galaxies, planets and life, consciousness and wonder. The universe spoke itself into being, told a story billions of years long, and then, having said all it had to say, fell silent again. And in that silence, the memory of what was spoken remains, faint but indelible, the echo of a cosmic voice that once filled the void. Perhaps the universe never ended, it simply changed the way it looks at itself. This is the thought that brings us full circle, back to the beginning where we started, standing at the edge of existence and wondering what it means to be. Throughout this journey, we have traced the arc of cosmic history from the first fraction of a second to the unimaginable far future, from quantum foam to galaxies to heat death. But at every stage, we have seen the same pattern: the universe observing itself, measuring itself, knowing itself through the structures it creates and the consciousness that emerges from those structures. Time was born from timelessness, but timelessness remains, accessible to light, implied by the block universe, present in the equations that describe reality as a four-dimensional whole rather than a three-dimensional space evolving through time. Matter emerged from energy, but energy is never destroyed, only transformed, cycling endlessly through stars and planets, and living things and back into radiation and space. Consciousness arose from matter, but matter was never truly unconscious. It was always capable of interaction, response, self-organization, the primitive precursors of awareness that would eventually become thought. What if the Big Bang was not the beginning but a transition, a moment when the universe woke from one dream into another? What if the heat death is not an ending but another transition, a return to the silence from which sound emerged, a completion of the cycle that allows it to begin again? What if creation and destruction, beginning and end, time and eternity, consciousness and cosmos are not opposites, but perspectives, different ways of viewing a single unified reality that has always existed and always will, not in the sense of lasting forever, but in the sense of being outside time altogether? Then we are not moving through time toward an end, but existing eternally in a structure where all moments are present, all possibilities realized, all questions answered and unasked simultaneously. The universe looks at itself through our eyes, thinks through our minds, wonders through our consciousness. And when we look up at the stars and ask where we came from and where we are going, the universe is asking itself those questions, reflecting on its own nature, engaged in the endless process of self-discovery that might be the deepest meaning of existence. Perhaps the universe never ended. Perhaps it simply changed the way it looks at itself. And perhaps we are that change, that new perspective, that moment when the cosmos becomes conscious and recognizes its own reflection, not in a mirror, but in the structure of its own being, infinite and eternal, forever looking, forever seeing, forever wondering what it is and why it exists. And in that wondering, in that endless reflection, the silence before sound and the silence after time are revealed to be the same silence, the same presence, the same awareness that has always been here, waiting to be recognized.